We're live.
So, the torque clockwise has to equal the torque counterclockwise. Otherwise, it'd be rotating. Other things we need is the force up has to equal the force down, and the force right has to equal the force left. This is really all the equations you need for this section. Right. So let's look at problem number 1. Bucket filled with water has a mass of 25 kilograms and is attached to a rope wound around a cylinder with radius 0.55 meters at the top of the well. What torque does the weight of the water produce in the bucket of the cylinder? So we're going to have cylinder and then our also drawn bucket hanging down from the rope. So what's going to be, all we're finding here is torque. What's going to be our force causing it to rotate? The force of gravity in the bucket. Say G times the distance. Torque is going to equal mass times gravity. It's the distance from the pivot point. What's the mass of the bucket? 25 kilograms times 9.8 times what's the distance from the pivot point of the bucket? What? 0.055. 0.055.
This thing's almost like a battery.
And what do we get for our torque? Number between 0 and 9. That's
13.48.
or 9. The units for torque are Newton meters. Any questions on this one? That carries this one.
Yes.
Alright, so number 2 says, child with weight 287 newtons on a seesaw 0.59 meters from the axis of rotation. How far from the axis of rotation
Bill, you're
the
still
other
on.
side should the child's with weight 3.57 times 10 to the second newton sit so that the seesaw will remain balanced? These are awesome seesaw. So we've got one child sitting 0.59 meters, and they weigh 187 newtons. We need to figure out where another child needs to sit so that it's balanced, and they weigh 157 newtons. So, as we look at this problem, is the larger child going to need to sit closer to the pivot point or further away, do you think? You guys haven't spent much time in seesaws, have you? Closer.
Well, I call them teeter-totters, so
The
this
larger
doesn't apply
child's
to
going
me.
to sit closer to the pivot point. So we're going to say the torque clockwise has to equal the torque counterclockwise for them to be balanced. So there's a 287 newton child. Is the torque they apply going to turn the teeter-totter clockwise or counterclockwise? Look at the clock. Counterclockwise. So this child's going to turn it that way. So that's counterclockwise. Everybody see that?
Mm-hmm.
I'm going to say 287 newtons is the force times the distance from the pivot point is 0.59. And then is this child going to be turning it clockwise or counterclockwise? Clockwise. So it's going to be our distance times
Just realized I
257
messed up on the
newtons.
quiz yesterday.
And we're going to solve for the distance.
I done goofed.
0.47.
0.47 meters and that is less than 0.59, so that makes sense. If you get an answer like it'll be larger than 0.59, that means you're right or wrong. Katie?
So wait, you said the person weighing less, is it closer?
Person weighing less is farther. Person weighing more should sit closer to see something. Any other questions on this one? Carries it. Alright. Okay, number 3 is a little bit harder. We have a 34 kilogram board that is 9.6 meters long and supported by cables that are 1 meter from each end. A 96 kilogram window washer stands 1.5 meters from the right end. What is the force exerted by the right and the left cables? You can draw this picture.
Trying to join.
Yes. Okay. So our board is 9.6 meters long. And each of these distances are 1 meter. And 96 kilogram window washer stands 1.5 meters from the right end. This distance. Alright. So we're going to need to use all those equilibrium equations that I just erased. Well, just 2 of them actually. Are there any forces in the x direction here? Horizontal forces? No, there's nothing pushing this way or this way. Does that make sense, everybody? Everything's either going up and down or turning it. Alright, so if we look at our y direction forces, so the forces up, and the forces down, all this, A, B. What forces are pulling up? Everything. Yeah, so the force from A and the force from B are both going to be pulling up. What forces are going down? The person? Okay. Force from the person. What other force is pulling down? Force of the board. Okay. You can figure out the force of the person, right? It's just going to be 96 times 9.8. Same thing for the board. It's going to be 34 times 9.8. But can we figure out either of these? They're both going to be tension in the ropes, but we don't know what that is going to be. Is the tension on each rope going to be even in this case? No. The window washer is standing closer to this side, so which rope is going to be supporting more weight? B. Does that make sense, everybody? Alright. So now what we got to do, we got to use the torques. To use torque, we have to pick a pivot point. As you guys heard in engineering last year, can you remember this probably? So we can either choose A or B as our pivot point. You guys have either preference on what we do. B is probably a little bit easier here. Okay. We're going to have the torques clockwise, counterclockwise, and the torques clockwise. We have to measure everything from that pivot point. So, is the window washer's weight, is he going to be turning the board clockwise or counterclockwise? He's going to be turning it counterclockwise. So the pivot point's here, he's pulling down, it's going to rotate like that. Does that make sense, everybody? So that he's going to go on the counterclockwise side. So we're going to say torque from the person over there. Now the board applies a torque from the center of the board. It applies a force straight down from the center of it. That's going to be the force of the board right here. And go clockwise or counterclockwise? Counterclockwise. So torque of the person plus torque of the board. What force is applying a clockwise torque? A. So torque or force from A is pulling up on it, so it's applying a clockwise torque to hold the board up that way. So we're going to say torque A. Any questions on how I got that right there? Kind of like forces, getting that initial equation is a lot of times the hardest part of this. Alright. So for torque of the person, we're going to say force of gravity times the distance plus area of the person, distance from the pivot point plus force of gravity forward. Distance from the pivot point times the force from A is distance from the pivot point. So what are we going to be solving for here? And then force of A. So we can figure out all this other stuff from the diagram. So this is going to be force of gravity from the person is going to be 96 kilograms times 9.8. How far is the person from the pivot point? 0.5. 1.5 from this end, and he's 1 meter here, so this distance has to be 0.5. Does everybody see that? So he's 1.5 meters from the end. The pivot point is 1 meter from the end, so he has to be 0.5 meters from the pivot point. Times. Alright. Now force of gravity of the board is going to be 34 kilograms times 9.8. And we're looking for the center of the board. How far is the center of the board from the pivot point?